All right, today we're going to be talking about the ideal gas law. Previously, we've talked about a couple of different gas laws that gave us relationships between pressure and volume and temperature and how gases behave when you change one of those variables. Today, we're going to talk about one more that doesn't so much have to do with changing one of those variables, but using them to figure out whichever one of them you're missing. All right, but first of all, let's go into a quick review. We have Boyle's law, which was the first one we talked about, and it's talking about the inverse relationship between pressure and volume. So as pressure increases, volume will decrease. If volume decreases, pressure increases, vice versa. Basically, when one of them goes up, the other one goes down. Okay, Charles' law is the directly proportional relationship between volume and temperature. So if temperature increases, the gases will want to expand, which causes volume to increase. And then the other way around as well. If temperature decreases, volume will want to decrease as well. When one of them goes up, the other one goes up with it. Okay, Gay-Lussac's law was the relationship between pressure and temperature, and it's also directly proportional, like Charles' law was. So again, when one of them goes up, the other one goes up as well. If you increase the temperature, the pressure is going to want to increase with it. And then last, we had our combined gas law, which basically took all three of those equations and smushed them together. And that let us solve these problems when more than one of the variables is changing at once, right? If we have pressure and temperature both changing at the same time, well, Gay-Lussac's law only has to do with pressure and temperature, and then Boyle's law has to do with pressure and volume. Charles' law has to do with volume and temperature, but if we change more than one thing, we need to use the combined gas law. That way we have all three variables in one equation. So the one we're going to be talking about today is the ideal gas law. And the difference between when we use this and when we use any of those other ones we talked about before is that these ones have to do with changing some of these variables and seeing how it affects the other ones, right? You change pressure and you see what that does to volume and temperature, or you change one of them and you see what it does to the other two. The ideal gas law we're going to use not when we want to change one and see what effect it has, but when we know multiple of these variables at one given moment and we want to try and figure out the last one that we don't know. So it's not so much about change between one time and another time. It's about at this moment, these are the conditions it's under, and we can use this to figure out whichever one we're not sure about. So the ideal gas law, the equation for it is PV equals nRT. So P is your pressure, and the pressure can be in any of the units we've talked about. You can have atmospheres, you can have millimeters of mercury, you can have kilopascals, whatever you want for pressure or whatever the problem gives you. You don't have to worry about converting it to something else. Your volume, on the other hand, has to be in liters. So V stands for volume. And if it gives it to you in anything other than liters, you've got to make sure before you try and do any of the math and plugging values in, you've got to convert that to liters. Otherwise, the equation won't work. All right, N stands for the number of moles of gas that you have. So sometimes the problems will be nice and they'll give you moles straight up. Sometimes they'll give you grams, and you'll have to go in and figure out based on the molar mass of whatever chemical it's asking about, you'll have to figure out how many moles it has. But that's a skill we've been doing for 2 months now, basically. So you should be pretty comfortable doing that, hopefully, by this point. Okay, your R is what's called the gas law constant. And it's just a value you're going to plug in there. And what value you use depends on the unit that you're using for pressure. So on the next slide, I'll show you a chart that has the different values of R that you can use depending on what your pressure unit is. But it's always going to be one of those three values. It's never going to be anything else. And then temperature is the last one, is T. And just like temperature in our previous gas laws, this one has to be in Kelvin. We can't plug in Celsius or Fahrenheit or anything like that. We've got to convert it to Kelvin first. All right, so this is your little table that has the different values of R that you're going to be plugging in based on what unit of pressure you're using for the problem. So when you're doing your homework, you might want to keep this slide handy so you can go back and look back at it and figure out which value of r you're going to use, at least until you get a hang of it and can remember which one goes with which. And then when you guys have your test on it, I will give you these values. You don't have to memorize them. So if atmospheres is the unit of pressure we're using, the value we'll plug in will be the 0.08205. If our pressure is in millimeters mercury or torr, we'll plug in this 62.36 for R. And then if we have kilopascals as our unit of pressure, we're going to plug in 8.314. Okay, so let's see how these problems actually look. All right, there's kind of a 5-step process you're going to want to go through in each one just to make sure you've got all of your values in the right unit before you plug them in. So the first thing you're going to want to do is convert your sample size to moles. All right, so in this problem, it's telling us we have a 4.22 mole sample of argon. So it's already done it for us, right? You're not going to have to do all of these in every problem, but you have to check them all and make sure they're all in the right unit. So in this one, it's giving us our sample size in moles. So we know it's just going to stay as 4.22. All right, the second thing you're going to want to do in every problem is convert your temperature to Kelvin. So in our problem here, it tells us that our temperature is 34 degrees Celsius. If you remember from before spring break, the way that we convert between Celsius and Kelvin is by adding 273. So we're going to take 34 plus 273, and that will tell us our temperature in Kelvin. All right, so that comes out as 307. Your third thing you're going to want to check is make sure that your volume is in liters. In this problem, it's asking us about the volume. So it doesn't give us a volume, so we don't have to worry about step 3 here, because whatever value for V our equation spits out will be in liters automatically. So don't worry about that. All right, and then step 4 is where we're going to decide which value of R we're going to use to plug in here. The unit of pressure in this problem is 1.21 atmospheres. So if we go back and we look at this previous slide, we can see that when atmospheres is our unit of pressure, the value for R is this one right here, 0.8205. Sorry if y'all can hear my dog chewing on the bone over there. So for the value of R, we're going to have 0.08205. All right, and then your last step is basically just plug and play. You're going to plug all these values in that we found for the respective variables in the problem and solve for V for volume, which should be the only one we don't know. So our P, the pressure, we're going to plug in 1.21. Let's say that's times V, because PV. Say that's equal to N, which is our number of moles, our 4.22, times our value for R, and then times our temperature in Kelvin that we found. All right, and once you get to this point, it's just algebra, right? Over here on the right side, there's no variables or anything, so there's nothing stopping us from multiplying everything together. So 4.22 times 0.08205 times our 307 gives us a total of 106.29905.7. And our left side is still the 1.21 times V. When y'all do these problems Y'all can feel free to round them down to 2 decimals to make your lives easier. I'm just leaving it whole here for the example. And then our last step to get the volume by itself is that we need to cancel out this 1.21 that it's multiplied by. So we're going to divide both sides by 1.21. So we're going to take this number divided by 1.21. And we should come out with our volume is equal to 87.85 liters. Alright, and your volume always is going to be spit back out at you in liters if you've plugged everything else in correctly. So we don't have to worry about changing units or anything here. Alright, so that's one example. The next one we're going to do, instead of giving us our sample size in moles already, it's giving it to us in grams. It says we have an 8-gram sample of H2 gas. So our very first thing we're going to have to do here is convert this mass to moles. Alright, which means we're going to need to look at our periodic table and figure out the molar mass of H2 as a compound. So if we come over here and look at the periodic table, we can see that hydrogen has a molar mass of 1. And then the formula for this gas is H2, which means we have 2 of those hydrogen atoms. So 1 times 2 is 2. Alright, and then if you guys remember, anytime you're converting from mass to moles, you're going to divide the mass of your sample by the molar mass of the compound. So here we're going to have 8 grams divided by our molar mass of 2. So we come out with a total of 4 moles of hydrogen gas, of H2. Okay, the temperature, the Kelvin. The problem this time is asking us about the temperature, so we don't have to worry about step 2 here. We can cross it out. Convert the volume to liters. It's giving us our volume in liters already. It says I have a volume of 53 liters. So we're good there. And then on this one, if we go and look at which value of R we're going to be using, we need to notice that our pressure has units of kPa. So it's in kilopascals, which means that if we look back at this chart, we're going to be using this value here, the 8.314, as our value for R. Alright, and once we figured all that out, all that's left is to plug stuff in and solve for our temperature. So our pressure is 229. We're multiplying that by our volume, which is 53. We have our N, our number of moles we found was 4. We know our value for R that we're going to be using in this problem is 8.314. And we know our temperature is what we're looking for. So that's going to stay as a variable, as T. Alright, so we can start combining terms here. 229 times 53 over on the left side comes out as 12,137. And then if we combine our terms over here, we have 4 times 8.314. And that's 33.256. And remember, that's still times our T. We didn't combine that yet. And then in order to get T by itself, we need to cancel out this value here. So we're going to divide both sides by our 33.256. So 12137 divided by 33.256 gives us a temperature of 364.96 Kelvin. Alright, so that's what y'all are working on today. Ideal gas law problems. You've got your homework assignment to work on, and then once you get that done, you just make sure you've gone back and completed all of the other gas law assignments, because those are the ones that are going on this current 6 weeks progress report. Let me know if you have any questions.